Okay, this is our type 1 and type 2. This will be our first video, and really this is just going to be a review of concepts. So this is going to be our first video having to deal with concepts regarding errors. So first off, we're going to talk about p-values, which we've been using all the time. And just as a review, first off, please remember it's a conditional probability. And by definition, and here's the definition of it, the probability of getting a test statistic as extreme or more extreme, given that the null is true. In other words, if we were setting up a fraction, remember given is always in the bottom. And so in this case, it'd be given HO, the null is true. How likely would we get a sample just like this? How likely this sample? And this is actually an important concept, and it goes like this. If the null is true, how likely am I to get a random sample that produces an output like this? Am I very likely, or am I a little bit likely? And so when we calculate a p-value, which we've been doing when we run a hypothesis test, we get a percentage. If it's a big percent, it's like, hey, it's really likely that we'd get something like this. If it's a small percentage, it's really unlikely we'd get it. And when it gets so small, we don't believe the null anymore. It's kind of like this. When someone claims that they make, 35 points in a game, and you go to the game and they make 30 points, and you're like, well, maybe on average he does make 35 points in a game. But on the other hand, they claim that they make 35 points in the game, and you go to the game and they only make 3. You're like, 3 points, and he's claiming 35. I don't believe him. I don't believe his claim of 35 is true. So basically, if you end up with a really small percentage, I mean, it can happen by random chance, but it's so rare that we just don't believe the null. Please note, the p-value is not the probability that the null is true. It's basically, here's our definition right here. So you probably want to label it that way. It's the probability of getting a test statistic this extreme by random chance alone that the null is true. So how do we use p-values to make decisions? Well, we come up with an alpha level. And remember, we have alpha as our symbol like this. We also refer to it as the level of significance. Okay. So we use alpha to make a decision with the p-value. In other words, whether we're going to believe or not believe the null hypothesis. Now, we don't like to use the word believe and not believe. We like to either reject or we say we fail to reject. So when the p-value is small or super small, it tells us that the data are rare given the null hypothesis. All right? It shouldn't have happened, in other words, if the null were true. And at some point we go, it's so rare we don't believe the null. And we can define a rare event, and we arbitrarily doing it, setting a threshold. And that threshold that we set is alpha, and we use alpha to compare it to our p-value. And remember, the alpha is, the threshold is called the alpha level, which you need to know that, which I think you do. Because we sit there and go, we take our p-value and we write alpha over here and we make a comparison, all right? So if our p-value is less than alpha, we go, you know what? We reject the null. I told you that's what we've been doing all this time. When we calculated the p-value, we go, hey, it's such a rare chance that we'd get something like this, we no longer believe the null. On the other hand, if the p-value happens to be greater than alpha, we fail to reject. Like what I did there, fail to reject. All right. We don't like to say we accept the null, so don't say that. Do not say accept. We just say we failed to reject. In other words, we didn't prove the null, but the data is not that rare, so we're not worried about the null being true or not. Now, alpha is a measure of risk. In other words, it can happen by random chance alone that we get rare data. And so if we set an alpha level of 5.05, it means 5% of the time we're going to reject the null, but we shouldn't have. But if we knew that, we'd go back and fix that. It's kind of like if you know you're missing a question, you'll go back and fix it if you know the answer. But we don't know that we made an error. It just happened by random chance that we got data that looked like this and we rejected when we shouldn't have. All right. Why did we get that error? Well, it's due to that error is due to natural variations. In other words, when you take a sample and I take a sample, because your sample, if we're sampling of the Reagan students, and you take a sample of 100 and I take a sample of 100 students, we're going to get different samples. And yours may say 60% like the fight song, and mine might say 55% like the fight song. And if that's the case, we have a difference. And as a result, we go, hey, you know what? Why did that district happen? They basically both did random samples. There shouldn't be any issues, but there's sampling variation. And because of the changes by random chance alone, we end up making bad decisions, or we incorrectly reject the null 5% of the time. All right. And we can use different alpha levels. In other words, you get to choose whatever alpha level you want to choose. And you're like, well, I don't like being wrong. I don't want to be wrong 5% of the time. Okay, choose a smaller alpha level. Choose 3%, 4%, 1%. But when we choose a small alpha level to minimize the chance of mistakenly rejecting a null, we can make a different type of error, which means we can reject the null and that be an error sometimes, or we can fail to reject a null and that's also an error. And so as one error, if you decrease one error, the probability of the other area goes up. Now, those two errors don't sum to one, but as one goes up, the other goes down. So as one goes up, the other goes down. And it's like, well, I got to balance it out. And generally speaking, that's why we usually choose alphas equal to 0.10, alpha equal to 0.05, probably the most popular. And then we also use alpha equal to 0.01. And you're like, well, when might I want this big alpha, the bigger alpha? Well, if I'm looking to find a cancer drug that's effective in treating cancer, I might be happy going, you know what, it's effective, and having a high big alpha. Why? Because we don't have a cure for cancer, so having anything would be helpful. 5% is typical because generally speaking, we're fine making a 95 on our test. In other words, if we're wrong 1 out of 20 times and we make a 95, we're generally okay with this. On the other hand, I might want a really, really small alpha if I'm like on a life or death situation. If the decision I'm going to make cause someone to die, I'm going to want to make it really small, probably even smaller than 0.01. All right. All right. Next thing. Next page. As I alluded to, we make errors. In other words, nobody perfect. Even with the best sampling techniques and lots of evidence. In other words, we have lots of data that supports our decision. We still make error. We still make the wrong decision. And that error, as I alluded to, is due to sampling variation. In other words, because samples are different, they can impact. Everyone's sample is different. We can get different responses. Now, we can help minimize this error. We can minimize this error by increasing sample size. Increasing sample size helps a lot. But that's not always feasible. It's expensive and it's time consuming. But it helps. But increasing sample size Won't eliminate that error, but it makes it smaller. So what are our two types of error? Well, in statistics, we're really creative about things. So we have two types of error. One is called type 1 error, and we measure that by alpha, and we were kind of talking about that already. And the other type of error, and see, notice we were real creative, so wait for it. A type 2 error is the other type of error, and it's measured by beta or B. So alpha, the Greek letter alpha or A, the Greek letter beta or B. And when can you have made these? Because you can only make them one time. The null hypothesis is true and we reject it, type 1. So the only time I can commit a type 1 error is if I reject the null. So if I reject, I can make it type 1. May have, might not have. I might have made the right decision. On the other hand, if I fail to reject, I can make it type 2. If I reject, I can never make it type 2. If I reject, I can only make it type 1. If I fail to reject, I can only make it type 2. So it kind of works out, all right, that we have two errors, pretty simple. Now I say that the verbiage is complex, so that's why we're going to spend some time on this. So this is a typical box. You'll see this type of graphs in college. It seems like it shows up in every stats class and every textbook. So I'm using the same thing. So let's just say this is actual reality. It's the truth. It's what things are. This is over here is the decision I made based on my sample. So let's just pretend that the null hypothesis is true. If the null is true and I retain the null, in other words, I failed to reject, the null is true and I retain it, I did the right thing. I believe the truth. I made a correct decision. Yay me, that's a correct decision. I did the right thing. I believe the truth. I retained the truth. On the other hand, if the null is false and I reject it, I rejected a lie. So these two are correct decisions. Retaining the truth, believing the truth is good. Rejecting a lie is good. On the other hand, let's just say the null is true and I reject it. I rejected the truth, which means I'm now believing a lie. And so this is bad, all right? Over here, the null was false and I believed it. So I also here believed a lie. So you have two things. You can make it, if it's true, you can believe it, and that's the correct decision. If it's true, you can disbelieve it, and that's a wrong decision. If it's a lie, I can believe it, bad decision. If it's a lie, I can reject it and not believe it, and that's the right decision, okay? Once again, these things that are off to the side right here, super important. If we reject, the only type of error that we could commit or might commit is a type 1. Of course, we might have made a correct decision. All right, we could have made a correct decision. If we fail to reject, the only type of error that we might have made or could have made is a type 2. And once again, we could have made correct decisions. We could have rejected, all right? Here we failed to reject, that was a correct decision. Here we rejected, and that was a correct decision. But you can also fail to reject and it be a mistake, and you can reject and it be a mistake. Okay. Hold on, rejecting. These are labeled incorrectly. This should be labeled as a, if they retain the null and the null is false, this is a type 2. This should have been a type 1. This is a mistake right there. That's, sorry about that. I need to go back and fix this. This should be labeled a type 1. This should be labeled a type 2. I'll get that fixed. Okay, alpha is the probability of committing a type 1 error. All right, alpha is the probability of committing a type 1 error. And we've already talked about that. And that means I rejected and I shouldn't have. I rejected the truth. We've already addressed this, so I'm going to skip that. You can read it yourself. Beta is the probability of committing a type 2 error. All right. And this time we did not reject. We believed HO and it was wrong. It was a mistake. How often is a type 2 error? Really, really very difficult. We'll never calculate it. Now, one thing to notice is alpha goes up, beta goes down, but alpha plus beta does not equal 1. All right. As alpha goes up, beta goes down, beta goes up, alpha goes down. But the two of them, if you add them together, they do not equal 1. They equal less than 1, but don't worry about that. You can't calculate. If I give you alpha, you can't calculate beta. If I give you beta, you cannot calculate alpha. However, there's another thing, and we'll talk more about this in our last video. Power of the test. The probability of correctly rejecting a false null. Hey, this is doing the right thing. This is doing the right thing. I rejected and I was supposed to reject. I rejected and I was supposed to. In other words, power, we rejected the hoe and that was the right thing to do. All right, we rejected the hoe and it was the right thing. So power is correctly rejecting the hoe. Now, power does equal 1 minus beta. Power does equal 1 minus beta. So if I gave you power, you can calculate beta. If I give you beta, you can calculate power. All right. Also, we can, and this part we'll talk about again in our last video, we can increase the power of the test by increasing the sample size. And there's an inverse relationship between power and type 2 error. So once again, power up, beta down, and vice versa. Okay. Also, that also means if we're power going up, beta going down, that means alpha is going up. So power and alpha move together, beta moves the opposite direction. All right, thank you for that video. And please remember, I will fix this in your notes. This should say type 1 here. This should have said type 2 right there. Thank you.